Okay, so what I want to do now is give an overview of the methods that we'll use for doing analysis in a little more detail than just than what we just did. And in particular, we'll look at some of the concepts and the governing equations in a little more detail. So this business of translating a concept into an analysis, I've got an example here that I did a few years ago. And so here's the concept. This thing right here. This is a cross section of a gold mine in South Dakota, and it's a pretty impressive place. See, you see that thing right there? That little blue thing. So you know what that is? Does it say? You know what that is? It's my scale bar, and that's the Empire State Building for scale. So this is a humongous place. It's over a mile deep, and each one of these is a layer or is a level where they did mining. So here's some shafts where they went down, and then they went and these are tunnels. And if we look down on it, this right here is a map, and there are like hundreds and hundreds of kilometers of tunnels in this place. So the question was, this place started in like the 1880s, been there for a long time, and the question was, how does it affect fluid flow uh, in the area? That this is dry, so there's some big pumps down here that were pumping water out. So how does it affect the fluid flow? What about contaminants? Contaminants. How might contaminants be affected by this thing? And then also the stresses and perhaps well, stresses and strain, shall we say, the deformation. How would this thing affect the stress field? Okay, so those were the questions, and what we wanted to do then is to come up with an analysis that would allow us to address that. So here's the approach. Now, pretty clearly, I think, uh, we're not going to be able to simulate this whole thing. Each one of these is a tunnel, and it would be great if we could have each tunnel in there, but that's a lot of tunnels. I mean, this is a simplified diagram, and even then, look at all those tunnels. Maybe at some point we could, but right at first, that's way too complicated. So we need to come up with a more simplified version of that, and this is the strategy. So here's kind of the overall procedure, and the first thing that we start with is the geometry. So that's the slide that we just saw, and what I did was to say, well, this thing here, that's way too complicated with all those levels. So what I'm going to do is say that we've got a region here like this, where the overall average properties are different than out here, which is just intact rock. And if we look down on this, it looks kind of like that. So there's this kind of 3D region that's kind of going in like that, where the properties are different. And so here's the model. And this thing right there, that's this mine, this big huge mine. And these are you can see each level here. So we traced out what the mine looked like at each level, and put it together. But the properties are just averaged out. And so that's a big simplification of the geometry that we did, just to make it tractable. And then this thing here, this doesn't really exist. This is just to help us define the mesh. And then this last step that I had down here is the mesh itself. So you can see that this green region is just a place where the mesh is a little bit finer. So there's the geometry. It's a simplified system. Once we do that, we have governing equations, and so here's the governing equation for transport in that system, and then here's some boundary conditions. So we have governing equations and boundary conditions and initial conditions. The parameters. What I mean by that is here. That's a parameter right there. That's the diffusion constant, and and there it is. So we define parameters like that, or I guess it's yeah, just diffusion, um, and then we discretize it and can solve it. And so we did that, and we have some other governing equations for the fluid flow and for the deformation. And yeah, so here we go. Governing equations, boundary conditions, parameters, and dimensionless numbers. So the governing equations are going to be something like this. Boundary conditions will be something like that, and parameters would be guys like this. And that's going to be what we need to do to set up the problem that we solve. So the key thing, and what we're going to do every time, is have some governing equation, something like this. And that'll be what describes the processes that we want to solve. Okay, so one thing that we're going to do with this class is really cover a bunch of processes. Each week, we'll have a different governing equation. So there'll be a lot of them. But what I've tried to do to make it tractable and to make it accessible is that each one of these governing equations starts from the same place. So we got 15 different governing equations, but really there's just one. So it's kind of a nice approach. It kind of helps you unify how these governing equations are working in your own mind by having a common approach, and really it'll be a common starting equation. And so the basic concept, well, so all of these governing equations are what are called conservation equations, and we'll start with kind of a basic general conservation equation. And these kinds of governing equations really are just an embodiment of some basic rules that we are going to say apply to the process. And the conservation rule is perhaps the most important. And the strategy is to define a control volume. So we have some kind of a region, this blue region, and we have some stuff going in and some stuff going out, and there's some stuff stored in here. And so this is the simplest rule, that the rate going in equals the rate going out of the control volume plus the rate of change of the stuff that's in there, that's stored in there. Okay, that'll be the basis for these conservation equations. So what we'll do is apply this rule to some fundamental quantities, and there'll be a variety of possibilities here. Probably conservation of mass is the most common, and most of what we'll do a lot of what we'll do will have a mass conservation component to it. One version of mass conservation could be just the mass of a fluid, or mass of something that fills the entire region, but you also might have mass that is dissolved within the fluid. So those will be pretty common with the things that we'll do. We'll also, though, conserve momentum for fluid flow problems and deformation problems. That'll be important. Conserving energy is for what we'll do. We'll conserve heat energy, and electrical charge is another possibility, and there'll be a special case where we'll conserve volume. Okay, so those are the different options, and here's what we're going to do. This is kind of the overview, and then I'll show you some more detail here in a second. So we'll start off, we'll have something that's going to be conserved, and I just showed you half a dozen things that we'll consider. And we're going to define that on a per volume basis. Okay, so if we're conserving mass, we're going to then define it on a per volume basis, so it'll be mass per volume. And then we've got stuff going in and stuff going out, and we'll define those in terms of fluxes. We'll have the possibility that things that this thing that we're conserving is created or destroyed. So those will be described as sources. And we'll also have the ability to store or to change the storage of this thing that's conserved within the control volume. Okay, so we need to be able to identify what these different things are. And then we'll apply this conservation rule, and that'll allow us to kind of put things together. We'll in some cases use constitutive equations, and constitutive equations, these will tell us how materials behave. So there'll be, when we're looking at fluid flow, that'll say, it'll tell us some aspects or some properties of the fluid that we'll need to consider. And then we'll mess around with that stuff there, the conservation laws and the constitutive equations, and that'll give us, we'll mess around, simplify or refine, and that'll give us the equation that we want to have. Okay, so that's the big picture. What we'll do for each week is this. We'll go. Part of the lecture will be this stuff. And so what I want to do now is well, we'll look at this in a little more detail. So the step one here is to identify what kind of quantity we're going to conserve, and then put it on a per volume basis. So in the notes that I handed out, and the notes that I will use for the class, I've tried to keep a consistent nomenclature and format. And so I'm going to use this term here, capital theta, for the quantity that's conserved. Okay, so this would be like mass or momentum or heat. And then we need to define this on a per volume basis. So we've got the quantity, and we're going to define it on a per volume basis. So if we've got a control volume like that, little cube, then that is LC, the characteristic length of the control volume. So lowercase c is the stuff that's conserved per unit volume of the control volume. Now this is going to be, this little case c is the dependent variable. So what that means is we're going to set up our analysis, and we're going to have equations. The thing that we're solving for in the equation will be lowercase c. The thing that we would measure, if we were going to do an experiment, this little lowercase c is what we would measure. Okay? So we want this to be a general strategy. Here's how it's going to work. If we have mass, and let's call this mass of a continuous phase. Okay, so the control volume would be completely filled with water, for example. It's continuous. So then our theta would be mass, and we would have, well, let's, so C would be mass over, and for the continuous phase, the mass over the volume of the phase, that is, actually, you know what that is? Mass over a volume of like a fluid? Density. Yep. So if we want to conserve mass and it's a continuous phase, like a continuous fluid, little lowercase c is going to be density. Okay? We might also have a situation where it's mass, the mass is conserved, but it's dissolved. And so in that case, it's C and mass. It's going to essentially be the same, but this will be concentration. Another possibility. So momentum is mass times velocity. So I'm going to use a lowercase v for velocity. So that's momentum, and we will write it on a per volume basis. So it's mass times velocity per volume basis. And so one thing we might recognize is right here, this guy right here is density. So we could write that like this. The product of density and velocity is momentum. Okay, so there's our dependent variable for those kinds of problems. Well, we can conserve energy. What we'll do is conserve heat. So what we're expecting is that C will be equal to heat energy per unit volume. And the way we're going to write that is like this: Cp rho times theta. So let's see. Let me define, just for clarity, that V, that's velocity. So down here, Cp, that's heat capacity. That's density. Well, I guess, density we've defined, so we don't need to write it here. And then see this skinny theta? That's lowercase theta, and that's what I'm going to use for temperature. I'm not going to use T for temperature because I'm going to use that for the basic units of time. And I'll show you that in just a second. But let's just check this. Heat capacity. Heat capacity is going to be the energy required to raise a unit of mass per some degree, some amount of temperature. Density is mass per length cubed, and this lowercase theta is in degrees C. So we can check the units here, and so this thing here is got units of energy per volume, and so that's going to be, that grouping of terms will be what we'll use for the dependent variable when we do heat problems. Okay. Uh, Also, we have charge. So this will be the C will be units of charge per volume, and electrical charge is like coulombs, and so that would be charge density. Okay, so there's a setup for various different things that would be conserved, and translating them on a per volume basis to quantities that will analyze. All right. Now, uh, when I did the overview, I noted three main types of processes: a flux, source, and storage change. So let's take a look at those things. So flux of a quantity is going to be the concept is that we have some stuff, cap theta, the stuff that we're interested in conserving, and it's moving, and it goes through this unit area, um, and it does that in a unit of time. Okay, so that's the concept of flux. It has units of this, whatever we're conserving per area in a unit of time. Okay, and we'll have two kinds of flux that we'll be interested in a general way. Advective flux, which is where the stuff we're conserving is moving with a flowing fluid, and diffusive flux, where it's moving in a static fluid. So we'll be interested in both, and they'll have different ramifications in the different processes. I'll use this symbol here. That's capital gamma, and that's going to be the total flux. Okay, so that's both advection and diffusion added together. Okay, so we'll have one possibility for our balance or our conservation is that we've got a control volume, and then in here we've got some kind of way that the stuff that we're conserving is created. Okay, so one way to think about this is if we're interested in the mass of a certain molecule, we could have a reaction internally that creates that molecule. And so we're creating this material that we're conserving per volume in a unit of time. Okay, so the way to think about it is that the source is the rate of change of the quantity that we're analyzing, C, and C, of course, is cap theta over volume cubed. So this ends up being that the source is, that's a unit of time. So the source has got units of this. Okay, so this is basic units. Sometimes when I write basic units, I'll put it in a square bracket like that. But this is basic units of time, a capital T. I'll use capital M for basic units of mass. This is the reason why I don't use, why you have to use that little lowercase theta for temperature. Well, as it turns out in our class, we'll deal with temperature and heat transport a little bit, but time we'll deal with every lecture. So I wanted to reserve capital T for time. Okay, so sources will be important, certainly for some processes. Storage change. So when we have processes that are transient, that are changing with time, the thing that we'll be interested in is having some material in here in our control volume, and the amount of that material that's stored in there will be changing with time. Okay, so we'll express this storage change as a time rate of change of our dependent variable, lowercase c. So this storage change, it's going to have the same basic units as a source. It's going to be our stuff that's being conserved per unit volume, changing with time. Okay, so those are the main concepts. Now, what we want to do is put this together to develop a conservation law. And this is the concept here. And it's pretty much this concept that we had a few slides ago, except I've added in here this rate produced by the source. So the first time that I showed you it, we didn't have that, but we see now that including those sources will be important, so we'll call it out explicitly here. And the way that I set this up is everything on this side is in or being produced, and everything out here, this is leaving or changing in storage. Okay, so this is the rule, and what I want to do is use this rule to come up with what will be an equation that is basically the equation for the course. If we were to make a t-shirt for the course, it'll have this equation on it. Okay, so it's done out here, but I think it's going to be easier. Hopefully, it'll be easier to follow if I just draw it out and explain what's going on. Okay, so let me see. I'm going to do this over on the side here. So here's the control volume. And so we've got some flux coming in, and flux is per unit area. So the rate at which stuff is going in is going to have to be the flux times the cross-sectional area. The cross-sectional area there is delta y, delta z. So the rate of stuff going in is that. And then we've got some flux going out. And we multiply by delta y, delta z to get a rate of stuff going out. And then we've got an internal source here, so the stuff that's being created. Sorry about that. And that's going to be multiplied by the delta volume, and then we've got a dc dt, the storage change, and that's also delta volume. Okay, so let's put that stuff together. First of all, let me define a delta volume as delta x times delta y times delta z. And these deltas are the dimensions of the control volume. Okay, so our balance says that the rate going in is this. It's the flux coming in times delta y, delta z. And that equals, let's take a look at that. That's going to be units of theta L cubed, or theta is, or I'm sorry, gamma. Gamma has those units. These are L squared. So this term here has units of our the stuff that we're conserving per time. So those are going to be the basic units in our balance equation. So there's the first term. We're going to add to that the sources created, and that'll be times delta V. Source has units of that's the units of the source, and delta V has units of L cubed. So we're good with the units. That's going to be theta out. I'm going to get rid of that. Need a little more room. So theta out, delta Y, delta Z, and the storage change. Okay, so this is the manifestation of our balance rule. Then what we do is apply Taylor series expansion to first order is that the flux coming out is the flux coming in plus the change in the flux with x times delta x. Okay, so this is just from calculus, and this is going to go in there. So what we get then is, I'm going to write this out again. So I'm going to write this out with the substitution. Okay, so now, let me see. I'm going to switch colors, and so now we multiply through by these terms, so we'll have right there delta Y, delta Z. And what we'll see then is on this side we've got the flux in times that area, and here this is the same term. So these cancel. And then this delta x, delta y, delta z, that's delta V, the volume of the control volume. Okay? So now we've got S delta V, the gradient in the flux delta V, storage change delta V. So the delta V's cancel. And so now we have this. Okay? All right, so now this is just doing it in one dimension. So we've just considered the flow in this dimension. If we also make it 3D, we would have flow in Y. And if we go through this and do it for Y, then we get, this would be flux in X, X, this is X. If we do it for Y, we essentially repeat all these steps, except right there, instead of X, we'd replace it with Y. So if we do it for X and Y, then we just generate another term like this. So this would be, if we did it for 2D. And if we do it for 3D, Oh, sorry. Okay, so there it is, 3D. We've got Flux bringing stuff in. Basically, it's the change in the flux, the gradient in the flux. There's the storage change. There's a source. So we can write. This is a vector. So if we take the divergence of a vector, we get that. So these terms here are that. So we can simplify all of these guys and write this equation like this. Get rid of that stuff. So we give this guy a little bit of room, and we can put a box around it because that's the final conservation equation. That will be essentially, this is the terms for conservation and a control volume of in a generic way. We're writing this without really specifying what we're conserving, so we think it's going to work for a variety of different quantities. Okay, so actually I see that we're out of time. This will be a good place to stop, and we'll pick this up next time.